Hello, everyone. Welcome to our CARES webinar. It is 2 o'clock, and I suggest we give it another minute or so to let some other people join, and then we will start the meeting in a minute. Welcome, everyone. Welcome to our City Air Remote Emission Sensing webinar, the CARES webinar at the end of the Horizon 2020 CARES project. Let me start with some housekeeping rules. My name is Peter Mock. I'm the Managing Director of ICCT in Europe, and I'm happy to host the event today. As a participant, you are at the moment muted, so we cannot hear you. And we will first go through a series of presentations from our speakers who I will introduce in a minute. And then after we are done with the presentations, you will have the opportunity to raise your hand and ask questions. And we will then have plenty of time in a panel discussion to answer any questions that you might have. Let me introduce our speakers for today. So we will start with an introduction from Åke Sjödin. Åke is from the Swedish Environmental Research Institute, IVL, and is the coordinator, the lead of the CARES project. We will then hand over to Johan Bernard. Johan is a researcher, senior researcher at the International Council on Clean Transportation, and he will tell us more about the practical lessons learned from the remote emission sensing work carried out in the CARES project. Our third speaker will be Kaylin Lee. She is with the International Council on Clean Transportation as well, and will present us on the analysis side, on the key results from the analysis side of the project. Then Jens Borken will take over. Jens is with the Technical University of Dresden, and he will tell us more about use cases for city and government officials, and in general outlook and next steps regarding the project results. And then as a last speaker, we will have Peter Lilienberg from Gate 21 to tell us more about the NEMO project, another Horizon 2020 project. And then, as I said, at around 3 o'clock, we'll turn it over to a Q&A session, and you as the audience, as attendees, you will have the opportunity to ask questions. Again, you will be muted for the presentation time. If you have any questions in your control panel that you should see, you have the opportunity to already type in questions now or during the presentations. You can simply type your question. It will pop up here on my end, and I can bring up those questions later on when we come to the Q&A session. Or you can raise your hand at any time, and we'll know that you want to say something or you want to ask something later when we come to the Q&A session. For now, I would ask all speakers to close your cameras, shut off your cameras, and Åke, you leave on your camera, and I will hand over to you, make you the presenter, and ask you to give us an introduction to the project. Okay, we cannot hear you yet. 1 second.
I hope you can hear me and you can see my screen.
Yes, all good.
Okay, thank you. Yes, I'm going to give you an introduction to the CARES project. After 4 years of hard work, of which 2 were during a pandemic, we're very happy to share with you some of the results from this exciting project. I would like to start with the history, where we come from. Sorry, I have to. where we come from in the history and where we're heading. So I think none of us would be in this webinar if it hadn't been for Professor Don Stedman at the Department of Chemistry at the University of Denver, who invented the first remote sensing instrument in the late 1980s. Unfortunately, he's no longer with us, but his spirit lives on in many ways. So the first remote sensing measurement campaign in Europe took place in 1991, that's more than 30 years ago, where my institute invited Don Stedman to Gothenburg for a pilot study. We measured in 3 days in September emissions from about 15,000 gasoline passenger cars on a freeway ramp in Gothenburg. That was only a few years after that the three-way catalyst had become mandatory on new cars sold in Sweden. And we found that this seems to be a very useful tool. We could see very clearly that the new cars had much lower emissions of carbon monoxide when the three-way catalyst became mandatory. Also hydrocarbons dropped sharply. And a few years later, we did the first measurements on NO, and we can see that this was a success story with the three-way catalyst on passenger cars. Then the development of the remote sensing technique at the University of Denver moved on. So in 2007, we were one of the first to include also NO2 and be able to measure NOx emissions. And these are the results from the measurements we did then. We can see that the passenger cars to the left here, they had steadily improved their emission performance. And this was maybe also the first look into the diesel problem, which has extended and expanded in quite a few years after that, and not least with the Dieselgate. So in 2016, those of us who were involved in remote sensing research in Europe decided it's time now, when we have so much data, we should try to pool these data to make them even more useful. And this was the start of the CONOX project and the start of building the CONOX database, financed by the BAFU in Switzerland. And I would say that this is also what was the starting point for the CARES project, because 1 year later, the first call started to circulate, and we put together a consortium and we wrote a proposal which was successful. So we could start in 2019. And now the consortium consists of 20 partners from 11 countries, of which 3 partners are from China. We have also, we have also had the pleasure to, include the 2 primary remote sensing service providers in globally. That is Opus RSE in Madrid and HEAT from the USA. So this was really a good team of remote emission sensing and RDE expertise starting working on this project. We have partners from universities, from research institute, from NGOs and small enterprises, and also cities, of course. We committed ourselves to do a 3 measurements campaign in Milan, Italy, Prague, Czech Republic, and Krakow in Poland. So, and you may think, why do we care about this? Of course, it's the air quality and all other environmental problems related to air pollution emissions. And this, I would like to show you the key messages of a very recently published report, only a few weeks ago, from the EEA. And it's the key messages of their analysis for 2023 is that we still have a major health concern for Europeans regarding air pollution. We are looking much into fine particulate matter, which is one of the still persisting large problem related to air quality and health. And we also see that Central Eastern Europe and Italy were the ones reported the highest concentration of these pollutants. And all countries reported levels of nitrogen dioxide that are above the health-based guideline level set by the World Health Organization. And you can find this report on the web. Yeah. So the overall objective of CARES is to reduce the hurdles for applications of remote emission sensing, we abbreviate it to RES, to make it a widespread means of both monitoring and enforcement of vehicle emissions. And ultimately, this will lead to cleaner air for all. If you're looking at the detailed objectives, there are a few. We want to be able to measure the effectiveness of specific policies and measures by means of monitoring vehicle fleet emissions under real-world driving conditions. We want to be able to detect vehicles with tampered or malfunctioning emission control systems with high accuracy to enforce emission regulations by prosecuting infringing vehicles. Also on our agenda was to develop 2 innovative, non-commercialized, non-intrusive RES measurement techniques that can be used in conjunction with the commercialized RES equipment. And of course, we gather a lot of data in all remote sensing studies, so there's also a need of standardized data management and RES databases. That's been a part of the development as well. We want to reduce barriers for deployment of RES across the European Union through demonstration of the developed measurement techniques and the data infrastructure in 3 polluted cities. We'll come back to that soon. And also, not least, that since this is an international cooperation flagship project, we want to reduce the barriers also for deployment internationally through collaboration, in particular with China. Yeah, so with this, I come to my final slide, my introduction. This is an imaginary image of the CARES cloud computer platform over database. I will not go into any details, but there is a new database coming up that will replace the CONOX database, which has become a bit old. We will be able to provide in this database up to maybe 2 million records by the project end later this summer. And we have developed 3 types of apps that can connect to the database and make various users, stakeholders interested in data to access the data. So most interesting for you at the moment may be the public app that we have developed, and it's also up and running. So you can go there and click and approach the database. I will just show you what happens when you click there. You come into the user guidance to where you can select the city, you can select different plot types, and you can find out about emissions from different types of vehicles and so on. So I think this is a good introduction to what we're going to present in the next hour. So with this, I leave the floor to the next speaker, maybe Peter there in between.
Thank you very much, Åke. Indeed, thank you very much for that introduction. I hand over now to Johan from the ICCT about the session or the section on remote emission sensing measurements in practice. Johan?
Hello everyone, I hope you can see the slides now.
Yes, all good.
Perfect. Great, thank you so much, Åke and Peter, for the introduction. It's a pleasure for me to present you some of the practical lessons learned of the campaign, more specifically the city demonstration campaign. I think what we can just summarize is that it can be done right in the cities. You have here 3 pictures. The first one is the testing that we did in the first time in Milan, followed by testing in Krakow, and finally in Prague and also Brno. Overall, over than 300,000 valid measurements were collected. And I think this is another reason to call that a success. And for that, I also like to thank all the partners that were involved, as we saw around 20 different partners who led to that point. So we talked briefly about remote emission sensing, but I need to give you maybe a sort of a short introduction if you're not familiar with the technology, and talk about the different types that exist. So first of all, you have commercial, often called open path or optical remote sensing technology that can measure real-world emissions of 1,000 cars per day. Those use a light beam or a laser beam to capture snapshots, 1 second snapshot of exhaust emissions from an individual vehicle passing by. So vehicle pass by, that light gets, part of it gets through the plumes, and then as a function of the absorption of that light, once it reflects back on the mirror or on the reflective strip, you get an idea of how much pollutant you have in that plume. You get about up to 10,000 valid records per day with that technology. That means that you can measure a vehicle every 3 seconds, basically. Very importantly, for any remote sensing technology is that it is very important to collect the license plate of the car or of the vehicle that you measure, because then that allows you later to make the link between the car and its specifications, such as model, make, first date of registration, emission standard, etc. And that's of course true for the other type of technology. So here are the two technology that we tested, one from Opus Remote Sensing Europe, which is this crossroad equipment, and then from the HIT company, the EDAR system that capture vehicle emissions scanning from the top down. Then other type of non-commercialized remote sensing technique. This is similar in the sense that this is contactless, but however, in that case, part of the plume is actually, part of the diluted plume is analyzed as it is rerouted towards analyzers. And that allows you, for example, to look at things that would have been difficult with the light-based system. For instance, particulate number. Often when particles are very, very small, they don't scatter the light, but then using those type of analyzers, you can have a good idea of the particulate number of those vehicles. This technique can be used, let's say, in two different use cases. One is maybe similar to what we saw before in point sampling. So that means it's sitting next to the road on the pavement, and it's actively sampling the air next to the vehicle as close as possible to the tailpipe. And then you have the plume chasing configuration where you have those analyzers installed in a van or in a car, and you're following another vehicle, often a truck, and you're measuring as the vehicle drives, maybe up to 1 minute or 2 minutes. In that case, of course, with the plume chasing, you can only measure, let's say, 200 vehicles per day because you need to follow those vehicles. And for point sampling, it's a bit less than it is less than the commercial system, because you need to make sure that you do measure the plume of that vehicle and not of the next one or the one previously. That means you need enough time, roughly 5 to 6 seconds between the vehicle. That means up to 3,000 vehicles per day. So let's go to the first testing campaign that was in the middle of COVID, September 2021 in Milan. In that case, we tested the HIT system, but also the point sampling. Primary objective was to track the effectiveness of the low emission zone, or zones, I should say. In Milan, you have 2 zones, area B and area C, with different stringency. The goal was also to compare the variety of remote sensing technique. So on that picture, you see the EDAR system from HIT installed. You have point sampling analyzers installed in the van, and you also have a car passing by with equipped with PEMS, with portable emission measurement system. In addition, that street was selected because it had air quality monitoring station, and our partner and colleague Amat were also experimenting advanced sensors. So we selected that location very specifically to meet the objective of that project. In addition, the University of York conducted some testing on point sampling of volatile organic compounds. And I would say some of the lessons learned of that preparation is that it was indeed a challenge to put that all together. I think our colleagues from Milan will talk more about this, but basically what was quite difficult for that campaign was getting the permission and access to the electricity, because those devices, for some of them, needed to be connected to the grid to run 24 hours. So that was really the most important challenge. Another challenge that we overcome is to make sure that there is no safety hazard, meaning if you put something on the street, you have to make sure that bicycled or people won't just step on it and end up with issues. And finally, GDPR for data privacy protection is also important. So that means you have to collect only the information that you have to. There is no point in collecting, for example, the color of the car. License plate also have to be taken and dealt with very, I would say, carefully, and cannot be stored in any way. You have to hash, so anonymize the license plate, and you cannot just do what you want with those. So other thing was also to make sure that people knew about the testing happening, so publishing information about the testing before it started and during it was conducted. You have here another picture of the testing that occurred in Madrid and the city center. What else to say is that, the point sampling was also used to look at black carbon, which is part of the particulate matter, and also particulate number, and Kaylin will present some of the results later. This is here as a sort of a zoom in of the point sampling. Just as I mentioned, you are actively sampling the air. So what you see here is the pipe that is used to get as close as possible to the tailpipe without getting too much onto the road. And what you see here is a light barrier, which is used also to detect when a vehicle passes by. Here you see the other locations. So surrounded in yellow is the Chilea, where we had also a second unit of the EDR system. And again, one of the vehicle equipped with PEMS passing by. And the second location was in Bazzoni, where additional point sampling testing was conducted. I invite you to look at the report once we'll have it on the website, because in addition, our colleagues also from AMAT tested, as I mentioned, advanced sensors compared to the reference air quality station. And there's a lot that can be said, showing the good agreement between those two, but also how the point sampling and EDR data were correlated, what is the emissions were collected with the emissions measured from those stations. As well as ammonia, if you're interested in ammonia concentration. A few more words about Milan, just a sort of a beginning of the analysis, but Kaylin will take over. This is the fleet measured by the EDR system. You can see a vast majority of passenger car. Which is also interesting is that we captured a significant share of LPG and CNG vehicles relative to other cities. We'll have some lesson learned on them too. And what you see, the other graph is the validity rate. So you don't get a valid record each time you measure, because, for instance, the vehicle could be decelerating when you do take that snapshot. But generally speaking, you get a 75–80% chance to capture the emissions of those vehicles. We must say that for that testing in Madrid-Rovini, let's say the instrument was not put in an optimal way, because we had to also conduct point sampling and to be in that street, etc. So that led to also maybe suboptimal capture of light vehicles, such as two-wheelers or three-wheelers, which ideally would be measured on a uphill driving. But yeah, that's how it is. That's also the real life of conducting testing. And also I would end up by saying that small vehicles like that might have also they do have a weaker prudence than other vehicles, which makes it a bit more difficult to capture. Krakow, a few words about the second campaign that was conducted in the middle of, in winter 2021. In that case, the Opus system, the crossroad equipment, was used as well as point sampling. A bit of context about low emission zone in Krakow, because the city had introduced a sort of a pilot test some years ago, and it's worth also mentioning that the national law has evolved to make it possible for cities in Poland to implement such a policy. Krakow announced about 6 months ago that they will introduce the first low emission zone in Eastern Europe from July 2024, fully introduced in 2026. And we really wanted to use the remote sensing data as a key data source to inform policymakers. And Kaylin will present a bit on the lesson learned on that part too. We also compare the data to the one collected in May 2019, which was a campaign conducted in summer. So more to say also in the report around those comparisons. But that's all. Yeah, I'll talk about the lesson learned, the practical lesson learned. So as I mentioned, this was winter, so it was a lot of actually a lot of snow end of November, pretty unusual, but that turns out to be really difficult to measure during those heavy snow moments. Because yes, heavy rain or heavy snow can impact the light-based measurement. Not such the case for point sampling, because you're actively sampling the air, but for light-based system it can. But more importantly, which is true for every remote sensing technique, you need to measure the license plates. And when you have dirt or snow covering the plates, there's nothing you can do. You cannot read the plates, therefore you cannot connect the data to the vehicle specification. So that's a point that we thought to mention, because it is one of the practical hurdles that we encountered during this winter testing. So here also we conducted testing using the Opus system, but also in some locations we co-located the instruments. So you can see here the Opus system as well as the vans from the CARES project. In Czech Republic, we tested all different systems, well, the Opus crossroad open pass optical system, the plume chasing, and the point sampling. I'll focus here, well, yeah, I'll add a few more information about the collocation of the point sampling and the Opus remote sensing testing, but also more information about the plume chasing. So plume chasing, if you recall, is when you have a vehicle with lab-grade analyzers following another vehicle, looking at its emissions. In that case, we had a sort of a simple setup with the van from Erinx equipped with just the NOx, NO and NO2 and CO2 analyzer. You see the equipment at the back of the van here. It's pretty small. It's actually in use by the Danish police. Then you have a more of a prototype advanced van in which you have a lot of more expensive lab-grade analyzers, such as SMPS to a counter, particulate size counter, and particulate number and black carbon as well. So just to sum up, yes, we had measurement on NO, NO2, particulate number, black carbon, and we also conducted enforcement campaign, meaning that vehicles were being chased, meaning heavy-duty vehicles were being chased, and once they were found to be suspicious or high emitters, they would be stopped and inspected by not only the police, but also expert, OBD experts that were then willing to and happy to connect to the car or to the vehicle, and so to the truck, and to understand why those high emissions are happening. Is it because of tampering? Is it because there is a defect? And more will be said by Kaylin also on that point. In practice, that means that yes, we involved the traffic police service department and NOx consulting expert, as well as a support from TÜV Nord, and also that part was funded by TU's Dresden. So you follow the truck, you have a live view of the NOx emissions, in that case of the truck, and you have a sort of a red, yellow, and green lamp based on thresholds that will tell you if this is a suspicious vehicle or not. Over 1,000 heavy-duty vehicles were measured, and in some cases, yes, manipulation were found. This is a AdBlue killer or AdBlue emulator that was found, among other issues in those vehicles, explaining the much higher emissions. So I'm at the end of the presentation. Major practical lesson learned: optical or open pass commercial system point sampling and plume chasing can be successfully deployed in cities. There are challenges such as electricity to the grid, access to the grid, or testing authorization, safety, GDPR, and eventually also access to the vehicle registration data, which might take 1 to 5 months. Plus winter conditions can be also a hurdle, but things can be overcome. Crossroad and overhead commercial system and point sampling, all of them were compared with reference instruments such as PEMS. You have more in the report. But the point here is that we needed to compromise on the testing location when you do want to measure all of them together, because they have different trade-offs, for example, on how many cars per day you can measure. And finally, plume chasing can detect highly emitting vehicles, but to do an enforcement campaign, you need to be sure that you do it in conjunction with the police or tempering experts. Otherwise, you do find high emitting vehicle, but you cannot just use that to enforce and over a fine. You need to know why this vehicle was a high emitter. So I'll stop here, stop sharing my screen, and I will hand it over to Kaylin.
Thank you very much, Johan. So for these practical lessons learned, I will remind you as the audience that you're still muted, but if you have any questions, you can always type them into the questions box that you have in your control panel, and then they will be collected for later. Or you just wait, keep your questions, and then you can raise your hand later. So now I will hand over to Kaylin, and Kaylin will focus now more on the analysis side on assessing the real-world emissions from vehicle fleets. One second, Kaylin. There you go.
Hi everyone, you should be able to see my screen now.
Yes, we can see it.
Great. So today then I will focus on the main findings from the remote sensing measurements taken in the 3 cities of Milan, Krakow, and Prague. And more specifically, this presentation will focus on the general emission trends identified for key pollutants, so nitrogen oxides and particulate matter, and the implications for the low emission zone policy, and also practical application of remote emission sensing techniques in high emitter detection. So when we look at emission trends, we usually focus on the emission standard level. In the context of the EU, we're looking at Euro standards, as you see here. That's because each new standard is introduced with new regulations, such as the emissions limit. So what you see as the yellow dotted line is the type approval limits, the limits that new vehicles have to meet before being allowed on the market. And the red dotted line refers to the on-road emissions limit, which was introduced from 2017 for Euro 60 temp and Euro 60. So overall, we see a good improvement of emissions, NOx emissions over time for all fuel types, so diesel, petrol, and LPG. And if we look at each fuel type, so for diesel, we see small improvement before the introduction of Euro 6 standards over here. So you see that all real-world NOx emissions are much higher than the type approval limits. But from Euro 5 to 6, there's a good reduction in NOx emissions. It's about 60% reduction. And Euro 60 temp, with the introduction of the road driving emissions, that's when the on-road emission limits were established. It helps the emissions from the preceding standard. So we see a good improvement in the newer diesel vehicles. For petrol fuel type, we see a steady improvement with newer standards over time, meeting all type approval and on-road emissions limits with the new 60 temp and 60 standards. And another novel finding that we had during this project was the NOx emissions from LPG vehicles. So we found that LPG vehicles, we commonly believe that LPG vehicles are cleaner than petrol, but from the real world measurement, it shows that especially for Euro 4 and 5, LPG vehicles had 30% higher NOx emissions than petrol vehicles of the same standards, so for Euro 4 and 5. We also looked at average NOx emissions by campaign. So by looking at campaign-specific NOx emissions results, we can add city-specific context to emissions characteristics. So what's sticking out here is the highly elevated NOx emissions from Prague's petrol and LPG emissions. And those are also seen, this is the average NOx emission, and these were also seen for median NOx emissions for the Prague petrol vehicles. And this is possibly due to poor maintenance and some loopholes in periodical technical inspection in Prague. And then we are further investigating this with the local partners over there. We also looked at particulate matter emissions from all measurements from the 3 cities. So for diesel, we see a huge decrease in PM emissions with the introduction of diesel particulate filters, which was introduced from Euro 5. So we see around 70% reduction in PM emissions for Euro 5. And from Euro 6 and above, they further achieved over 50% of reduction in emissions. For petrol, they are historically not responsible for PM emissions. They show around 20 to 40% levels of emissions that diesel vehicles emit for the older Euro standards here. And for LPG vehicles, we also see that there is no significant particulate matter benefits compared to petrol vehicles, contrary to conventional beliefs. We looked at particulate matter by campaign as well. And what stands out here is the Krakow PM emissions. So compared to Prague and Milan, Krakow's petrol vehicles emitted much higher real-world PM emissions. And this was largely due to the colder winter conditions that we had during the measurement collection. So this is probably largely due to cold engines that we saw. And another remote sensing method, point sampling. The data from point sampling also showed similar trends. So what you see here is the results for black carbon, which makes up the majority of PM emissions from vehicles. So for diesel vehicles, we see that mean black carbon emissions from Euro 5 standards and above. So these are the standards that are equipped with diesel particulate filters. They showed mean emissions all above the type approval limit of 5 milligram per kilometer. And we see that actually the median values are below the limit, which indicates that there may be a presence of a small fraction of high emitting vehicles that are pulling the average up. And for petrol vehicles, we see again highly elevated black carbon emissions from the Krakow petrol vehicles, as you see here. And when compared with the type approval limit, they were also above the 5 milligram per kilometer limits, but then most of the median values are below, which indicates that there was also a small fraction of vehicles that were emitting extreme values. For the second part, we find that remote sensing measurements can also support the planning and assessment of low emission zone policies. So as Johan already introduced, Milan introduced their low emission zone back in 2019. So they have 2 different restrictions for zone B and C. And I just wanted to highlight here that they exempt LPG and CNG powered vehicles, as well as 2-wheelers such as motorcycles and mopeds, which are very commonly found in the streets of Milan. And Krakow is introducing their low emission zone in 2024. They are distinguishing different vehicles registered before 2023 and then after 2023 to put different restrictions. So for all vehicles, the low emission zone restrictions will start from 2026. So remote sensing measurements provided evidence supporting the low emission zones targeting diesel vehicles. So as you see here from the NOx emissions pre-RDE Euro 6, which means Euro 2 to Euro 6, diesel vehicles had NOx emissions multiple times those from vehicles of different fuel types, and especially in Chile, Euro 4 diesel vehicles that do not come with diesel particulate filters accounted for 30% of PM emissions with only 3% of activity. And in Madre Cabrini, actually most of the Euro 4 vehicles were equipped with DPF, but they still contributed most to the PM emissions because they're only putting low emission zone restrictions from 7:30 in the morning to 7:30 in the evening, only on the weekdays. And current LEZ also exempts LPG and CNG vehicles as well as motorcycles and mopeds, as I said before. And these LPG vehicles actually emit higher NOx emissions than petrol vehicles, as we found in earlier results. And these vehicles are also responsible for high levels of carbon monoxide emissions. Those can be found in our report. And this was further complemented by a mobile point sampling method, which identified motorcycles and mopeds as important volatile organic compounds sources. So as you see in the left-hand side, motorcycles and mopeds have higher VOC and CO2 ratio. That's 5 times the passenger car value. And this is due to the high share of motorcycles and mopeds in Milan, as well as them using the specific fuel type, petrol and oil, which has 7 times higher VOC ratio than other fuel types. So Krakow's low emission zone is planned for 2026 for all vehicles, whereas Milan's low emission zone is already implemented. To quantify the impact of that low emission zone in the Krakow fleet emissions, we first projected how the fleet would look like in 2026. So when we only look at the 2021 measurements from the CARES project, it seems like over 21% of the drivers will be affected by the low emission zone. But when we projected, including the fleet renewal and fleet retirement assumptions, only 7% of the passenger cars in, here we go. 7% of the passenger car fleet will be affected in 2026. And these 7% of the fleet will be responsible for over a quarter of NOx and PM emissions from all passenger cars. So this demonstrates big emissions benefits the Krakow low emission zone would bring. So we were also able to demonstrate ICAD instruments capability of NOx high emitter identification. This was done with the support of the local authorities for roadside checks. So the total of 900 trucks were chased over around 2 weeks time. And the instrument was able to auto-classify with these thresholds if certain vehicles are emitting suspicious levels, high levels, or low levels of NOx. So we found that majority of the followed trucks were Euro 6, followed by Euro 5, and approximately 40% of those vehicles were tagged as suspicious or high emitting, and over half of those trucks, the trucks from countries outside of Czech Republic, showed high emissions, which called for inspections. So this plot showing here is comparing the daytime measurements with nighttime measurements. So the trucks with high levels of measurements were mostly driven at night, possibly to circumvent inspections. And for Euro 6 as well, higher share of trucks with high emissions were driven at night. And this was followed by the roadside inspections that identify the causes of high emissions. So total 17 vehicles were stopped. Quarter of them were suspicious emitters, and the rest were high emitters. And here, as you see, over 80% of the trucks had some sort of issues, including defect, software issues, and manipulation, and then around 12% was due to cold engines. And you'll see that for Euro 5, more of those vehicles were emitting at high levels because of manipulation, and then for Euro 6, most of them are because of software issues and defects. We also did a similar experiment with PN counter. So with point sampling, it could also complement technical inspection. So here, point sampling was used to flag certain vehicles with high levels of PM emissions, possibly due to malfunctioning or defective DPF. So that's the threshold, PN threshold that was used for this method. And as a result, 13 out of 17 vehicles were identified as PM high emitters. And there are some caveats that are identified. Unlike the ICAT instrument, this one doesn't have like an interface that auto classifies vehicles by emissions. So that called for some better software. And just to give you an example of the result. So this is a result sheet from the inspectors. So 13 vehicles were identified as PM high emitters. And to just take an example of EFWO, this was registered in 2014, possibly certified to Euro 5 or 6 with the DPF, but showed a PN number that was over 7 times the threshold. And it turns out that it had a expired technical inspection and was emitting at high levels. Just to sum up quickly, some major findings and conclusions. Most of the highest NOx and PM emissions were from pre-Euro 5 diesel vehicles, but since then there was a big improvement in emissions performance. We see that there were elevated PM emissions from petrol vehicles in winter conditions. LPG vehicles were emitting at higher levels than petrol equivalents, especially for NOx emissions. And we also see that a small share of vehicles were responsible for high average pollutant emissions, as shown by campaign-specific results. And for the policy implications, these remote sensing measurements can be used to quantify identify benefits and shortcomings of low emission zone policies and help make the case for it. Also, these techniques offer promising solutions to identification of high emitting vehicles or to support periodical technical inspections of vehicles in the European Union. So thank you for your attention. And I think I went over time a little bit.
Thank you, Kayleen.
Let me stop sharing my screen here.
Next speaker is going to be Jens Borken from the Technical University in Dresden. Jens, I'm making you the presenter now, and you can take over.
Thank you very much. I will go in presenting mode, and you tell me whether you can see the slide.
Yes, we can, but not in the right mode. So if you can just switch, because we see the
all right.
The mode. No, still, I think you need, there's a button.
Like this?
Yeah, perfect. Now it's okay.
Great. Thank you very much. Let me give you some views on how to use remote sensing in future and maybe for some outlook. I would like to focus on 4 issues, namely using remote sensing for what has been used in the past so far with very good success, namely to determine representative emission factors for fleets, for emission standards, vehicle categories, and subclasses, as we have seen and you may have seen. And that is pretty important for air quality planning, for making this rational and effective and having good models. That's also useful for policy in order to be effective. The other thing would be something related to in-use vehicles and their in-service conformity and monitoring emissions from vehicle subclasses to see whether they develop some defects over time or whether they are not well tuned from the beginning. And the finer you can go, the better you have an input for then further inspection. And this will improve the inspection effectiveness from just random sampling to predetermined pre-selecting by a factor, easily factor 5 to 10, what we have seen. The other thing that Kayleen mentioned, policy effectiveness can be evaluated, for instance, at the example of low emission zones, but also looking at the introduction of new emission standards or new alternative fuels or technologies and seeing whether they deliver in real world what they have promised to do. And last, most tricky, but also important when general levels of the fleet are low, is finding the needle in the haystack, namely the few, hopefully few, high-emitting vehicles which contribute 5 to 10 times more than the rest. And thus, though they are small in numbers, they make a significant contribution, and hence removing them is a good way to improve air quality, and it's important for effective enforcement. And remote sensing can help here. 1, representative emission factors. Remote sensing is nice because we have a tool at hand that offers a mass sampling of vehicles without interference, without interfering with the vehicle, so it doesn't know it's measured, without interfering with the driver or the traffic. So it is non-obstructive. And that is good for measuring emissions by Euro class, for instance, by model year, by manufacturer, by engine family, and the more data that you have, the fine you can go by ambient conditions, for instance, the temperature and the infamous temperature windows, by driving conditions and higher or lower speeds, accelerations, by elevation and other things. We already have a good set of data. Therefore, to my mind, we should focus our attention on at least the following 3 things. I mean, monitoring the longer-term behavior of Euro 6D vehicles. At the moment, all evidence suggests that they are indeed low in terms of the NOx and all the other emissions. But the question is this durable in the longer term, beyond 2-3 years, or is it somehow deteriorating? I think this should be followed. If it is not durable, then we are in trouble with the air quality. We do not have enough real-world data from trucks. They are measured by PEMS, they are measured the engines on the engine testbed, but they are not very much well measured in the real world. And we have techniques at hand where we can do so. And trucks are important as a big contributor to total pollution. The background is important for determining the back levels where we have all our pollution soup, both NOx and fine particulate matter. And likewise, we do not have enough measurements from high speed, high load conditions, highways, not even from passenger cars. And we have first examples here where we can do it. We've proven that it's working, but we need more to understand this. Therefore, my recommendation is, why not getting a couple of countries together, 3, 4 every year, rotating in conducting low intensity campaigns to monitor this, exchange the data and rotate the next year around to shift the burden to, but also to cover different places, different fleets. That is important because, for instance, here, even in the same country, and I'm drawing from examples beyond CARES, in Berlin, remote sensing measurements in Berlin suggest high emission rates from diesel cars. Remote sensing measurement half a year later in Frankfurt suggest low emission rates. Same country, relatively similar fleet, different ambient conditions, different things. Remote sensing is able to zoom in. Able to zoom in order to provide good quality data for local policy making, but also to, for instance, here, validate whether the standard emission model used in Germany, handbook emission factors, is actually well tuned to the situation. And the comparison between observation and model is in most cases pretty convincing. In some cases, there are some questions to do so. So, and if this is not well tuned, or if the remote sensing measurement is not representative, that's a problem. But we can do this, and it's important to match this for good air quality modeling and air quality planning. And within CARES, I think the city of Milan has done a lot of work in order to use the results and feed this into air quality planning, and has done improvements on the road strength and also feeding back improvements on emission factor developments, which benefits Europe. Second use case, monitoring of the in-use fleet by smaller segments. For instance, by vehicle classes, and within the vehicle classes, Euro stages, and within this, we can identify even vehicle families which are performing pretty well, and vehicle families which are performing much worse than average. For instance, Euro 6D temp diesel cars, plotted here from the 3 campaigns of CARES, Krakow, Milan, and Prague data pooled together. The vehicle family is in our case defined as the manufacturer times the engine displacement. So the first top manufacturer here with lowest emissions compared both to the nominal limit value as well as to the RDE limit. Daimler, Chrysler, passenger cars with 1940 CCM. And there are other vehicle families which have a significantly good performance close to the nominal limit and definitely below the RDE limit. But there are other vehicle families which are beyond the RDE limit under the driving conditions that we have encountered and that we have measured. And if I was to advise the PTI or any in-service conformity agency what vehicle families to look for, I think the evidence is to look at those first, which are at the bottom end of the remote sensing, in order to check whether this is really complying with all the regulations or whether there is some problem. Honestly, in this case, the problem is even worse, because for the Euro 6D cars, the same engine family, Hyundai 1600, is also performing worst. So maybe there's something to look at, and definitely to improve the efficiency of inspections. Third application for remote sensing, namely tracing the effectiveness of policies. Johan and Kaylin have already pointed out to the cases of low emission zones where the inspection was, where the remote sensing was first, and then it could be determined the shares in activity and emissions at the same time, and how much this can improve when dedicated vehicle segments are targeted. We'd also pointed out at the case of Milan measurements that supposedly cleaner LPG cars do not, at least are not better than performing in their terms of NOx emissions than petrol cars. And that is a case whether they are should then in any case be favored by on environmental grounds or not. Similar issue, hybrid electric vehicles are supposedly advantages for the environment because they are driven on significant shares of electric drive in urban areas. That's the theory. But we can measure, we have measured in Milan, and we see that's only 20% of the time max where they have electric driving, so they are not with zero emission passing the measurement site, but at 90% of the times they have their internal combustion engine on, and whether this is still an advantage for the environment remains to be seen. Other issues are there, for instance, the durability of Euro 6D, or when it comes, Euro 7, whether they actually deliver on the road as we suggest, or for instance, the supposed software updates of the in-use fleets for cars. Similar picture as before. Engine families, so manufacture times engine displacement, and indicated here is just for information, average values of 250 to 500 milligram NOx per kilometer driven. And you can see that there are a good number of vehicle families which are certainly beyond 500 milligrams per kilometer on average driving in the conditions that we have measured. And maybe that's something to be checked, whether they have really done their software update or whether this is still compliant with all the regulations. And particularly also given that there are other vehicle families which are have only half or less that level. Fourth, purpose, most tricky but also useful, identifying individual vehicles. So far we've always looked at classes and groups of vehicles where it is good to have good statistics. Finding individual vehicles by remote sensing measurement is a particular challenge, because at least the open path, the crossroad, and the top-down remote sensing measurement have only snapshots of the emission plume where they pass by. And on snapshots, it's hard to base a good judgment. Therefore, the two other techniques that were investigated and have been successfully demonstrated with the CHAOS project to be able to find high emitters. The one is plume chasing, and it's best applied on highways following trucks, because there you have stable conditions, you have a bit large plumes, and you can find them, and trucks are supposedly under hot operating conditions, so anything that is above limits is certainly suspicious. As well, the plume chasing vehicle follows the truck for something like 15 to 60 seconds to make an assessment, and this is it's proven to be very robust. The weak point here is, how does the inspection take place? Will it only happen at a place several kilometers down the road, and where some police needs to filter out the suspicious truck and then being inspected? Or the much better example, as it is practiced currently in Denmark, the inspector is in the chasing vehicle and he has the authority to pull it out on the spot whenever he finds something. That is something just to be, say, operationalized in its use. When you want to find high emitters among light-duty vehicles, point sampling has proven its value. And Kaylin pointed to the demonstration campaign, which was done in conjunction with police in the Czech Republic. And again here, the issue is, yes, the point sampler needs to come from a research application to a nice designed turnkey product, but this is on the way. And it can have two sensors on both roadsides, so that the plume and the wind comes, whenever it comes from one or the other direction, is captured. All this can be done. The essential thing is, for me, that the administrative and the legal framework is such that there are inspectors capable of interpreting the data and knowing how to pull out the vehicle, reading the data, making the confirmatory roadside check, and having vehicle data ready at hand, as any police nowadays in Europe has when they want to stop a vehicle for driving offenses. With cross-road or top-down instruments, you have snapshots. Contrary to plume chasing and point sampling, where you have larger integration times over the conditions. Therefore, for the other techniques, in order to find high emitters, the recommendation is to deploy several instruments, maybe 3 or more in a row or in some line, so that you have with one pass-by several records per vehicle. And we have demonstrated that with 3 to 5 records, you already get a robust classification, whether it's a high emitting vehicle or not. And then this comes then to enforcement. Again, here, one bottleneck is how is the enforcement is done. The inspectors need to be there, and we need to have the technical data from the vehicle, whether it's old or new, gasoline or diesel, at hand. Otherwise, you can follow an example that is, I think, practiced in Hong Kong, for instance, where you have several sensors in a row, and when they are exceeding, the vehicle is exceeding a threshold, then the vehicle owner gets a letter in order to get it inspected. This can be also done. Now, how to do this? We are not alone. As Orca had said, the researchers have started a long time ago. This is not an exhaustive, but a nice summary of remote sensing campaigns that have been conducted around Europe. The 3 CARES campaigns situate here, but you can see that we have a nice coverage of different fleets and different conditions starting to have. Most is urban areas and very few Flanders, some in Germany, some in Switzerland, has been on highways, but that is certainly rather beginning than the end. So my recommendation would be, why not cooperate? Why not cooperate across Europe to coordinate, say, something like 4 campaigns every year? 4 member states or authorities get together, say, we want to focus here on trucks, we want to focus on highways, we want to focus on certain vehicle types which are prevalent in our country. We agree to exchange the data. We rotate next year across other states so that we have a kind of permanent low-intensity surveillance system that ensures that problems are detected without too much effort. Plus, dedicated campaigns when you want to find the 10 to 20% high-emitting trucks on European highways, plus dedicated campaigns to find high emitters, or to look into specific issues like aging, like elevation effects, like temperature effects, like specific vehicle classes that you do for PTI. In order to do so, you need a good statistics. In order to have a good statistic, you need to accumulate your campaigns. Otherwise, you are losing a lot of the value. Thank you very much.
Thank you very much to you, Jens. We have one more presentation from Peter Lilienberg, Gate 21, who will tell us more about our sister project, the NEMO project, also Horizon 2020 project. Peter, before I hand over to you, one remark to the audience. Please raise your hand already now. If you have a question, think about more questions, but raise your hand already now so that when we come to the question section, we can dive right into the Q&A section right away. But now, Peter, up to you. We are curious to hear about the NEMO project.
Thanks, Peter, and thank you so much for inviting me to give a very brief introduction to the sister project, NEMO. And I've only have very few PowerPoint slides, so hopefully you can bear with me as I share these. NEMO, yeah, stands for Noise and Emissions Monitoring and Radical Mitigations. It is confusingly similar to CARES. There are some dissimilarities, so I will try to focus on those rather than repeating what has already been said. So yes, the project is very much about remote sensing. It's also about mitigation, and it's also about policies. So in terms of remote sensing, we have created over the last 3 years an autonomous 24/7 system where we have combined emissions with noise monitoring. And we've also developed a central software, which we called Nautilus. In terms of mitigation, there are two different aspects of it. One is to develop a novel pavement type that has less friction with vehicle tires, and also with the capacity to retain microplastics from the tire, from the wear, and also absorbing noise. And what we have done at the moment is we've just tested the novel pavement, taking it from the laboratory in Spain, from University of Cantabria, to the world's largest pavement fatigue carousel in Nantes in France, where it's been tested. So during 2 months, we've tested the equivalent of 1 year of trucks driving past it, 17,000 trucks per day, for a whole year. And we're waiting very eagerly for the results of that. And then we will take you to Florence, to real environments and real roads, to see how it works there. The second aspect of the mitigation is what we call a multifunctional barrier. You can see the prototype in the image, which is currently located in Valladolid, in north of Madrid in Spain. It consists of organic material that can retain emissions. It can also absorb noise, and it also has some urban functionalities. Apart from, plant cases, you can also sit on the benches, etc. It's only prototype, and we're also awaiting the results from that. In terms of policies, we've also investigated how to best use the new remote sensing technologies, and also trying to agree on a definition what actually is a high emitter, because there is no standardized definition of this in Europe at the moment, which obviously causes a big challenge. And also, can we create within the EU a similar framework for remote sensing that is already in place for LECs, because otherwise it will not be legally possible to implement it. In terms of the consortium, just to give you a brief overview of some of the facts and where we're based. We've tested the remote sensing in the Netherlands, in Spain, in various locations, in Florence, in Italy, and we are also monitoring emissions and noise from trains and ships at ports. So those are some of the things that differentiated from CARES, I guess. And yeah, those were just some of the things. And I don't know, Peter, if there would be questions specifically for the NEMO project, because otherwise I will say thank you and hand it back to you and the CARES team.
Yeah, that's fair, Peter. So thank you, first of all, for your presentation. And then I will, first of all, ask everyone from the presentation, from the panelists, to show your camera again so that we can see the whole panel. And then turning to you as the audience, please raise your hand now if you have any questions regarding the NEMO project, so that we give Peter an opportunity to respond. Or otherwise, we'll move on with questions for the rest of the panel. Don't see any specific questions on the NEMO project, so well, wait 1 second. Not sure. So there's one question on how can you differentiate exhaust and non-exhaust emissions. I guess that is for the NEMO project, a question. So Peter, do you want to say anything about that?
I think I will have to leave that one. And I guess there will be others in the panel who can answer it better than me, because I'm responsible for the dissemination of the project, so I'm not a technical expert on it.
That makes sense. Then again, thank you very much, Peter. And then thank you for joining. What I will do is, Christoph, you asked the question, I will unmute you so you can just ask it directly and maybe also point out who of the panelists you would like to direct it to. And if you can say what organization you are from, that would be very great for everyone asking questions.
Yeah. Hello, my name is Christopher Gatsu. I'm the CEO and founder of Nano Technology. Maybe devote a specific technology to reduce the emission of brakes.
Christoph, it's very difficult to understand you. Can you speak up or turn up your microphone?
Yeah, I hope it's going to be better this way.
Yes.
I just said that I'm the CEO and founder of an engineering company based in France, which is named Nano Technology. So we developed specific technology to reduce at source the emission of brakes. And we know that today, brake emission is a quite important source of emission of particulate matters compared to the exhaust for Euro 6 and D vehicles. So my question is really, how can you differentiate both non-exhaust, including tires, and exhaust emission during the measurement you made?
Okay, so how to differentiate exhaust and non-exhaust emissions?
Yeah.
All right. Is there anyone from the panel who feels comfortable answering that question?
Yeah, we can take it. I can give it a start. Since I was the one to present maybe the sort of a explanation around this type of remote sensing technique. So you may notice that we always measure CO2, which is the sort of the reference gas that we use to then derive pollutant by fuel consumption or even by kilometer. So what that means is that combustion needs to happen before we take that as a valid measurement. So that's, yeah, that means that we think we measure tailpipe only, and that's sort of information is corroborated by the fact that our point sampling colleagues say that they don't measure, they don't see any significant change in the signal when they measure electric vehicle. So to speak, they are confident that they are measuring tailpipe emissions only. Then your question is, can we measure, or can we use those techniques to only look at non-exhaust emissions? So I can say, well, the non-exhaust is actually why, because non-exhaust could be evaporative emissions. Some remote sensing device can do that. They do detect HC, but they don't see CO2, so it must come from the tank, or so that's one thing. But when it's about tires and brake, I think one of the challenges is that you miss a reference point. You see a signal, you might see a signal, but then it is diluted. So what would be the reference gas? Because you don't have CO2, what would be the reference gas to be able to derive meaningful information from that signal? This is, to me, some sort of a challenge. I'm just curious if there are any colleagues that want to add more onto that. But yeah, just try to clarify that we reported tailpipe emissions, and we're confident that was the case.
I was just wondering if there's possibly someone from AMAT in the audience, because they have been working a lot on trying to estimate or measure wear emissions, suspension emissions, but maybe they're not in this meeting.
We have someone from AMAT. Colleagues from AMAT, please raise your hand if you want to respond or if you want to participate in the discussion. Okay, doesn't seem to be the case.
But I can just say one more thing, which is that it will be in the report, but AMAT colleagues did also conduct a campaign during which, in Milan, at the same time, during which they clean intensively the streets of certain streets in Milan, and they did find an improvement looking at concentration in the air of PM10 after the cleaning phase compared to sites where cleaning did not happen. So they linked not the remote sensing emission measurement, but they did link the average concentration measured by the air quality station, and they saw a decline in PM linked to the reduction of resuspension after the street cleaning. So that's also related to non-exhaust.
Okay. Christoph, I hope we could answer your question. And okay, do you wanted to add something?
Can I add, yes, to Christopher? We're actually running a national research project at IVL to develop a methodology to measure from individual vehicles the wear particle emissions. We don't know if we will succeed, but maybe in 1 year we will know. So can stay in touch.
Thank you. I would like to move on to the next question from, I hope I pronounce your name correct, Munisai. You had a question for Kayleen, and I unmuted you so you can directly ask your question. Munisai, can you hear us? Can you ask your question, please?
Yeah, sorry, I could not follow the name. Sorry. Yeah, I am Siddharth. I am a research fellow in Trinity College Dublin, Ireland. So I have a couple of questions for Kaylin. So I would like to know whether the point sampling measurements are obtained in grams per kilometer, or are they converted to grams per kilometer? And the second question is, how do you deal with the negative concentrations? If have you obtained any negative concentrations of certain pollutants with respect to CO2, and how did you deal with them? Thank you. Thank you for the talk.
Thank you. Yeah, I can answer the first question first. As Yuan just mentioned, similar to the commercial remote sensing technique, point sampling also measures pollutant emissions in relation to CO2, so exhaust plume. So the raw values will be in pollutant per CO2, and then in the post-processing, we convert then the values to pollutant per kilogram fuel burn, and then to kilometer traveled using certain assumptions of fuel consumption. And on the second question, yes, we see some negative values when we get remote sensing data, and then that's pretty typical since multiple vehicles pass the measurement point, and then if the plume of the vehicle previous to the vehicle that's measured is bigger, then the concentration could get to negative, and that's why internally we set certain thresholds for these negative values.
So if I could add to that question, so how much of an effect will the leader vehicle plume will have on the follower?
Could you repeat that, please? Which vehicle?
Yeah, so the vehicle that passed by, how much it affects the following vehicle plume?
Yeah, it depends on the dilution speed. I think someone else maybe in the panel can explain this better. I think it was part of a different work package result. I'm not sure if anyone from the panelists can answer.
I'm happy to answer, or I think, as you said, Kaylin, there's been some testing also happening on the test track as part of the work package 1, where also fake fumes were used to see that impact. And indeed, it depends, as Kaylin said, about the dilution behind the vehicle. Which is also as a function of the vehicle speed. The faster the vehicle goes, the quicker the plume gate gets diluted because of the vortex behind. And so that's one aspect, but also how close you are, or the distance between the car. And that's why it's important to make sure you have enough time, especially from the point sampling between vehicles, to make sure you have less of this impact of plume interfering.
Yeah, can I ask one more question, quick question? So I also saw in the presentation that you have compared it with PEMS, portable emission measurement systems, but like what were the results like? Are the remote sensing measurements completely different from PEMS, or are they matching? I would like to know that as well. Yeah, thank you for answering my questions.
Anyone from the panel?
I would say very simply, they agree quite well, at least to start with, for NOx, I think. And there's, of course, maybe a problem to compare the point sampling, measuring specifically the particle number or black carbon concentrations with optical methods, because there's a limitation with the optical method to measure particulate matter. Very short. I don't know if you agree, Johan or Jens or Kaylin. But we did some work on this, so there are in the reports we are going to publish soon. You can find results of these comparisons with different instruments. Yeah.
Yeah. Thank you. Thank you all.
Timothy De Vries, you raised your hand, and I will unmute you now so that you can ask your question to the panel. And if you could again say who you are, what organization you're from, that would be great. Timothy De Vries. I hope I pronounce it correctly. Can you hear us? And could you please ask your question?
I'm sorry, I was muted. Tim De Vries, Eastern Research Group in Texas, and we're doing work for the U.S. Environmental Protection Agency. I wanted to address Christoph's question about non-exhaust PM. We hope to be working on that in this coming year, but we have been working on, for the last 4 years or so, evaporative emissions, as Johan was talking about. The heat instrument in particularly is good for this, because since it measures the pattern of the vortex behind the vehicles, we can see the different sources from the tailpipe, or if it's evaporative emissions from other places on the vehicle. And then if we use signal processing techniques and a standard technique called blind source separation, we can separate those two plumes and then evaluate them separately to get the emission rates of evaporative emissions separate from exhaust emissions. So the idea for the PM, you do the same thing. If you have a remote sensing instrument that is sensitive enough to see any PM, you should be able to apply the same technique. Of course, one of the problems is you can have PM from different sources. You can have it from the brakes, or from the tires, or from road dust, and that means you're going to get a lot of signal from different places, and that would be quite a challenge. The other thing about the negative values, you had a question about negative values, and I just recently saw the TNO report about in Flanders, and I saw the same sort of negative relationship that we see, and we think again that there may be a technique using signal processing, and particularly characterization of the noise of the instrument, so that we could deconvolute the noise from the measured distribution to get a quite good estimate of the true underlying emissions distribution. We haven't done it yet, but we're going to be trying here in the next year or so. So maybe we'll be successful. Thank you.
Thank you, Tim.
Yeah, thank you. If I may add to that, yeah, all very good points. You did mention the different sources, tailpipe and non-tailpipe, and I think another difficulty in comparing PEMS with the remote sensing is that even though the emissions come from the tailpipe, some of it might be carried over by the vehicle itself and behind its wake, so the vortex behind. And so when you take a snapshot with PEMS and remote sensing, you might have also a difference in what you see, because the remote sensing system might not only just capture the tailpipe emission at that moment, but also from the past seconds. That's something also that was shown with simulation in a recent peer-reviewed paper, which makes it a bit more difficult to compare PEMS and the remote sensing system.
Yeah, I think that when you do this comparison of remote sensing and PEMS, you have to remember that those timescales, like you're talking about, are important. We traditionally think of remote sensing as being an instantaneous measurement of what's in the tailpipe. I don't believe that's what it is. It's more of an instantaneous measurement of what's in the vortex. And the gases that get into the vortex have been put there over a period of 5 or 10 seconds of vehicle driving. So if you want to compare remote sensing measurements with PEMS measurements and you use a test vehicle, I believe it's important to drive that test vehicle at a constant speed and constant engine load before it gets to the remote sensing unit. In that case, you probably have a good chance of getting a good match up between the PEMS and the remote sensing instrument.
Great, thank you, Tim.
Tim, I would be happy to talk to you more about this.
Certainly, I will send you an email. Okay.
Good, great connection. Dennis Pöhler, I'm going to turn it over to you. And I want to remind the entire audience, if you have more questions, please raise your hand now or post the questions so that we can use the remaining minutes for answering any other questions. Dennis, up to you.
Yeah, okay, thanks. Yeah, I just had one question to Jens about the point you raised that the different remote sensing campaigns in 2 different cities, like in Frankfurt and Berlin, you showed such different results in the Euro 5 diesel emission factors, which you would not expect because the vehicle fleet should be very similar and it's not such a long time period in between these 2 measurements. Would this not be maybe an effect of the point sampling or of remote sensing, that you have a snapshot and that you maybe have different driving properties at these 2 different sites, which create for some vehicles specific higher emissions than in other locations? Or do you think these could also be other reasons?
The key reason is temperature difference. And you also saw it if you look again at slides after the talk, that there is a bigger difference not only with Euro 5 but also with Euro 4 and Euro 6 D-Temp and others, or with Euro 6 D-Temp less. We know that Euro 4 and Euro 5 diesel cars are sensitive to temperature, and it was simply warmer in Berlin than at the time that it was in Frankfurt at the time of the measurements, and colder temperature means higher emissions. This explains the majority, and you could see this was also reflected in the modeling by handbook emission factors. They also capture the similar temperature effect, by the way, sourced by remote sensing measurements. And they matched it perfectly for Euro 4, and Euro 6 has 6B has such much lower temperature dependence, a little bit there. There was an issue with Euro 5. And minor issues with fleet, a little bit with driving conditions and accelerations and stuff like this.
So then we need to conclude for the future that we need to do campaigns on the same spot at different temperatures. Or if you want to have a conclusion for this city or for this region, you need to repeat the measurement at different times of year.
Definitely, we should have different ambient conditions. But this is in a way a historic, a legacy issue where we know that it is particularly prone for the Euro 4, Euro 5 diesel cars and NOx emissions, not for anything else. So, and not all evidence so far is that Euro 6 is much less, it's rather independent of ambient temperatures and a wide range of driving conditions. So therefore, I would not argue for repeated campaigns saying things, but we can use campaigns from different spots if we carefully filter and have enough data to do so on a robust manner. Because it's not just a single place where you measure, but you measure under a whole range of driving conditions, and from morning 10 degrees over 25 degrees centigrade in the midday and 15 in the evening. So you have a nice span of temperatures, and if you go to Sweden or to the UK, you get down to 0 degrees temperatures and rest. And if you make a careful filtering, as is done with PEMS and feeding into the model, you can transfer from one location to other locations. It's a matter of statistics.
Yeah, so we need to just include in the data analysis that there is some dependency on the temperature if we compare different cities, you need to correct
Absolutely.
that if you directly compare the cities. Yeah.
For NOx and diesel cars, that's crucial. Otherwise, we need to look for ages. We've also pointed out that deteriorated petrol cars have significantly elevated emissions compared to their new standards, and this needs to be taken into account. And otherwise, we've seen that elevation, so altitude, is different. When you measure in Basel or Zurich, the emissions are relatively low. When you measure at 1,500 meters altitude in Davos, emissions are factor 2 higher. That has been the case for up to Euro 5 cars, but probably not for the nowadays. But I wouldn't bet on it. I would better check it.
All right. Thank you, Dennis, for your question. Thanks for answering, Jens. To the audience, I don't see any hands raised, so this is your last opportunity. Please raise your hand, type in your question if you have any more. It's a great panel to ask questions. In the meantime, okay, I would like to ask you a question. You as the consortium lead, at the end of the CARES project now, does the work stop? Is it like now over, or will it continue? And are there any resources that you want to point out to authorities or other attendees today? What can they basically approach, or what do we leave with the CARES project for them to make use of in the future?
Thank you, Peter. That was a good question. I'll try to answer it as good as I can. Yes, I think what we have done in CARES is that we have provided a couple of tools, hardware tools and software tools. I don't think we mentioned Open CARES software. It's slightly related to the database, but not. It's also a standalone thing. So I hope that we can find ways to because there is also room for improvements, I think, to be done, and that this can be done both on the hardware side and the software side. I think it will be done, and then I hope cities, member state authorities, whatever, will make use of these new tools. That's my conclusion. There are a few EU projects. I think the NEMO project is not finalized yet, so it will be interesting to see what comes out of that, because it's combining both noise and pollutant emission. I think it's very interesting. There is an ongoing Horizon Europe project on L vehicles, motorcycles, mopeds, and that stuff, measuring also noise and emissions from the roadside. So yeah, I think that's what we can say at the moment. And of course, the project will live maybe most clearly live on through the new database that we have been just sort of completed and filling with data, and we will continue filling it with data, and of course encourage other actors, other stakeholders to contribute or take part or whatever in that. So yeah, maybe that's my message for the time being. And a lot of public reports will be made available in the next weeks or months from the CARES project, so you can keep an eye on our website, CARES project, and then you can find hopefully for you interesting reports to read more about this. And yeah, and we'll be happy to answer any questions you have also after the project has ended. Yes, we are, I think many of us will continue working in various ways, and so yeah, you can always contact the persons in the panel or those involved in the CARES project. You can find more information on the website.
Thank you. Okay. Yeah, to also underline that from my side, what you just said, okay, there's a website, CARES EU, And there you can find already a lot of reports that have been published throughout the project. And there's more to come. There's going to be a very nice final brochure about the project to be published. And there's a number of technical reports that are still under review at the moment, but will be published in the very near future. So keep checking that website. And as you said, okay, please approach us, anyone from the organizations included in the CARES project. I'm doing one last check. Okay, we have here the website cares-project.eu. Thank you for sharing that link, Susanna. And doing a last check here, I don't see any hands up. I don't see any questions. So I think all questions answered. And I suggest we end the meeting 5 minutes early. I thank all the panelists for presenting, for answering the questions. And I thank you as the audience for joining us today and for listening to this update on our CARES project. I wish you all a nice rest of the day, and I hope we stay in touch. Bye-bye.
Peter, can I say something?
Sorry, yes.
Yeah. Well, it's about if there are any in the audience who are members of the CARES Stakeholder Advisory Board or Scientific Advisory Board, I just would like to remind you that there's a second chance for you to come back to these topics in 20 minutes. So there should be a meeting invitation sent to you. And I hope to see you at 4 o'clock.
Okay.
Thank you.
Then, bye-bye now. Have a nice day.
Thank you. Bye.
Thank you.
Thank you.